Okay, so we're now live. We're going to give it a couple seconds for people to join us. But in the meantime, I'll thank our sponsors. So, then again, thanks to Quanex as presenting sponsor of the Marketplace by Windor. We also have our gold sponsors who are Everlast, Vecca, and ScreenCo. So thanks to you, all of you, for being active contributors to FanCan. So with that being said, today we're going to start our technical sessions, something that most of you have been waiting for. Without saying more, I'll let you go, Al. I think you have all that you know what to present, so I'll let you go.
Sure. Well, I'd like to introduce our guests today, our viewers, to Dave Goldsmith, who is co-presenting with me. This is subject matter that Dave and I have been working on together, collaborating on, exploring, and we're happy to share with you some new information, updated information you might have heard at our regional conferences, but also some new information related to glass design, especially for guard loads. So happy to have you here, Dave. Happy
Thank
to
you, Al. Always
collaborate
a
with
pleasure.
you. Yeah, pleasure to work with you too. So today we're going to talk about the glass design, the new thing, what's new in glass design in the National Code 2015. Some really new stuff and some old stuff that just needs to be brought to mind that maybe I think more and more people are encountering, especially if you do work on large buildings. So we're looking at two topics today, glass design for wind load and glass design for guard load. Now, we're just going to give you some clarity here. The information we're providing here is in good faith based on portions of the National Building Code, the 2015 code, and provincial codes based on the 2015 code, such as the 2018 Vancouver Building Code, the 2019 Vancouver Building Bylaw, the 2019 Ontario Building Code, and possibly the Alberta Building Code, Dave.
That's right, NBC 2019 Alberta version.
Okay, there we go. So this is information that should be code pretty much coast to coast, except for a province or two in Atlantic Canada that are still in the 2010 National Code. This information is provided to inform our members, window manufacturers and glazing contractors, about some less well-known provisions that apply to window glass design. Now, this information does not constitute design advice. And so we're giving you the introducing you to these concepts, introducing you to what is new and changed in the code. We do recommend that you consult qualified registered professionals for matters related to glass strength design. So definitely you'll want to talk to somebody that's qualified in your area, or it could be someone outside your area. There are registered professionals that deal with glass design. But basically, we're informing you of what's in the code so that you can be better prepared to have those conversations and to address glass design matters in your organization. So topic number one is glass design for wind load. And the 2015 National Code introduced two important changes to how we determine the wind pressures that are used for glass strength calculations. One of them, which really struck me as quite radical, is a 25% reduction in the factored hourly wind pressure for calculations that are going to be based on the Canadian standard CGSB 1220 M89. And the rationale for that is to return to the level of reliability in glass design that was in effect when that standard was published. So it was published in 1989, and at that time, the code based our glass design calculations on the 1 in 10 hourly wind pressure. In the 2005 code, they changed that, and they based glass design the wind pressures for glass design had to be on the 1 in 50 hourly wind pressures, which were significantly higher than the 1 in 10. As you can imagine, the 1 in 10 hourly wind pressures are based on a wind event that has a 1 in 10 chance of happening any given year. The 1 in 50 are wind events that have a 1 in 50 chance of happening in any given year. So those are likely to be higher loads, the highest load that would occur in a 50-year period. So that in the 2005 code, they essentially bumped up the rigor of the calculations. And in the 2015 code, they've decided to reduce that load a little bit to bring it down to the level of reliability they had in the 1980s when the standard was published. The second change is that it now allows the use of ASTM E1300 for glass strength design in Canada. And to accommodate these two things, they added a new factor for the calculations, a load adjustment factor. So today, part 4 of the code requires design wind pressures to be calculated using the 1 in 50 hourly wind pressures published in Division B, Table C2 of the National Building Code. The design pressure calculations in the Canadian supplement to NAFs are based on the same hourly wind pressures. That's going to become significant in a few minutes when we go into more detail on these calculations. And then the use of ASTM E1300, but the code requires you to use a different adjustment factor for each of the two standards. And the adjustment factors are there to account for the differences in how wind pressures are determined in the United States using ASCE7 and their ASTM E1300 standard. It's a different basis for design than what we have in the 2015 National Building Code. So the adjustment factors are there to ensure that calculations using either pathway provide an equivalent level of reliability in the results. What that means is you might not get the exact same glass makeup using either path, but they're going to be close enough as to be qualifying as code compliant. So this information is presented in Article 4361, which is titled The Design Basis for Glass. And it tells us we can design glass in conformance with the Canadian standard, CAN CGSB 1220, using an adjustment factor of not less than 0.75, or ASTM E1300, using an adjustment factor on the wind load of not less than 1. So essentially, for ASTM E1300, you're using the 1 in 50 hourly wind pressure data. With the Canadian standard 1220, you multiply that 1 in 50 hourly wind pressure by 0.75, essentially reducing it by 25% before you carry on with other calculations. And there's a note that applies here, which tells us about additional factors that have to be applied to this adjusted wind load before you can design with one of those standards. And this is the load factor they're referring to. Essentially, it's a multiplier of 1.4. Here, the value of W is your 1 in 50 hourly wind pressure. So you start off by multiplying your hourly wind pressure by 1.4, then you apply your adjustment factors. So here's what that looks
Actually,
like.
Al, first those were
Yes.
factored per A440S1, right?
Pardon?
So it's not the hourly wind pressure that enters into that equation. It's that times the adjustment factor and the exposure coefficient and the internal and external gust factor and pressure coefficients.
Right, but these don't these factors get applied before you do those calculations?
That's right. Yeah.
Yes. Right. So yes. So in other words, step 1 is your 1 in 50 hourly wind pressure. Step 2 is your load factor. Step 3 is your adjustment factor, right?
Correct.
And now you have a value that you can use with CGSB 1220 or ASTM 1300. Or, as we will talk about later, with the Canadian supplement values.
Sorry for the interruption.
No, it's okay. That's okay. We're being clear. So here's what it looks like. If you're going to be using the Canadian standard, you take your 1 in 50 hourly wind pressure, multiply by 1.4 by 0.75. In effect, you're starting out with a pressure that is just slightly higher than the 1 in 50 hourly wind pressure. If you're using ASTM E1300, you multiply the hourly wind pressure by 1.4. The differences in the adjustment factors, as we've said, between ASTM 1300 are essentially 1.33 times greater than you're using for CGSB 1220. This sounds scary, it sounds punitive, but it isn't, because once the calculations are done using ASTM 1300, you'll have essentially the same glass design. And as we've mentioned, this adjustment factor accounts for the differences in how the wind pressures are determined under the ASCE 7 and the 2015 code. So this leads us to an interesting question. And can we use the Canadian supplement to NAFs to determine, or as a starting point for determining these wind pressures? And this is something that Dave's looked into, and we've discussed it as well with Robert Jutras and also another fenestration engineer, David Vidotz of Berkeley of RDH Building Science. And so we've run these ideas by them, and they are saying that yes, this is appropriate, this approach. So we can use the values from the Canadian supplement, the design wind pressure that we get for selecting a performance grade. We can use that as a starting point for calculations if we understand what else has to be done to that number. And the calculations that are done for designing the wind load resistance of a framing system, Dave, this is what's called serviceability states design, right?
Correct.
So we're designing for the in-service pressures that the window is going to be subjected to. And we don't want the framing to deflect more than L over 175 under normal service conditions. So during the lifetime of the window, it's going to be subjected to these loads. And we're just analyzing it for deflection, not for failure.
Right. It gets a little bit more complicated than that, because in NAVs there is no deflection limit for class R and LC products, but a deflection limit is always required in non-Part 9 buildings that are being reviewed by an engineer, because they know full well that the assumptions in the glass strength standard is that the edges are supported rigidly enough not to deflect more than L over 175 at the specified design pressure.
And that's a really important point, because because when we design glass, we're designing it to resist a failure load. In other words, we don't want the glass to fail. When we're designing our window systems, we're designing them for in-service loads, and we kind of take the structural test pressure of NAF, so 1.5 times the design pressure, as the failure load condition for the framing system. But the failure load conditions for glass are defined in the code. And, and so it's a different approach for designing the failure of glass. But your point, Dave, is that yes, the glass design standards the engineers are using to design glass are based on the assumption that the glass will not deflect more than L over 175. So, so this is what puts R and LC class products into this weird category where they're technically allowed to be used, but whenever, if you're going to engineer the system, you can no longer allow them to deflect more than L over 175. So when engineers are designing buildings, they're designing some components to a serviceability limit state and other components to an ultimate limit failure state. And so the Canadian supplement is giving us a design pressure for that deflection analysis. the deflection at L over 175, and that's the pressure we're designing our products to when they need to resist glass, support glass in service conditions, but we need to design the glass to a higher load for a failure load. So how do we do that? Well, we can apply the proper factors to the simplified method, to the design pressure we get from the NAFS calculator in order to be able to use that value for glass design. So the way this plays out technically, and if this kind of gets confusing and you say, that's too much information for me, Al, don't worry about it. We're going to end up with just showing what the calculation looks like. But the Canadian supplement uses an importance factor of 0.75. So the formula for calculating wind load in the Canadian supplement is a simplified version of the formula in the national code. Is that right, Dave?
Sorry, I had to unmute. Yes, that's 100% correct. Yeah.
Yes. So there's the number of factors an engineer can consider in glass design can be quite large in the national code. And in the Canadian supplement, these have been simplified to essentially give conservative, safe numbers that don't require the participation of an engineer, especially for, let's say, Part 9 buildings. Would that be correct?
Yes.
Yeah. So when we're designing glass, though, we need to design to the ultimate limit state, where the importance factor would be 1. So the design load you're going to use for the failure analysis is going to be higher than the design load you're going to have just for the serviceability analysis. So if we take 1 divided by 0.75 is 1.33333. So essentially, we would have to multiply the design pressure from the Canadian supplement by 1.33333 in order to have a starting point value for the additional factors that we would use for the glass design. Here's some examples. So if we're going to design it to the Canadian standard, CGSB 1220, we could start with the Canadian supplement design pressure for the building location, for the height of the window, multiply it by 1, divide by 0.75, which it amounts to 1.33333. Multiply that by the 1.4 load factor that Part 4 tells us to use, multiplying it by the 0.75 adjustment factor, which Part 4 tells us we can use for CGSB 1220. And so if we apply that calculation to a DP20 window, we would have to design the glass in that window under the CGSB standard for a wind pressure of 28 PSF on the glass.
I just want to make a quick comment here, Al.
Of course, Dave. Yeah.
Those who are familiar with math will notice that the 0.75 in the denominator cancels out the 0.75 in the numerator. So basically what it winds up to in a simplified way of thinking about it is you could use the A440S1 pressure, multiply it by 1.4.
Correct.
And that would be the appropriate pressure using 1220 amp standard. But
Correct.
The way it's being described here is absolutely correct as to the way the code works. So we're just not showing you any shortcuts here because we want you to fully understand.
Yes, thank you. And especially when we compare with the ASTM calculation, because the same set of, when we apply the right multipliers, we do get a different answer. So for calculations using ASTM E1300, we still have to do the importance factor adjustment of 1.0 divided by 0.75 times the load factor of 1.4 times the adjustment factor of 1.0. And when you do this calculation, DP20 becomes a 37.3 PSF glass design pressure. So you would then be using a 37.3 PSF wind load for ASTM 1300 design for a product where the Canadian supplements design wind pressure would be 20. So this is just illustrating the differences in what we would call the input values. In other words, what number do I use now with my glass design for the wind load? In the case of the Canadian standard, you're going to start out with a lower number. In the case of ASTM, a higher number. Both approaches are designed to give you, in the end, essentially the same glass design. So it is possible to use the Canadian supplement to determine designed wind pressures based on the location, the terrain, and the height of the window. Those values can be used as a starting point for glass design in Part 9 buildings. These values could be used by manufacturers to determine the glass makeup for estimating and costing purposes on large buildings. But project glass design should be performed only by qualified registered professionals. Can you describe how that works in the real world there, Dave?
Yeah, so basically on non-Part 9 buildings, you need that third-party professional design and field review. But you also, as a manufacturer, really want to quote the correct reinforcement and glazing up front, because that's when the budget is established, and that supporting registered professional has not yet been involved in the project. So manufacturers such as Plygem do an internal review using the same methods to make sure that we're quoting thick enough glass and strong enough mullion reinforcing. And again, this is not the act of doing the engineering for the purposes of building code compliance and the code letters of assurance or signing and sealing shop drawings. This is just to make sure that you're quoting the correct products, because once that budget has been established, the builder has gone, they've got their loan, and any increases in cost, you're going to be held to your original quotation, believe me. So if you need to change to 5mm glass throughout the building and you're only quoting 3mm, well, then you're not going to make any money on that job. You're going to lose money. So we got tired of losing money and started doing our own internal reviews.
And this is helpful. This is helpful to know because the Canadian supplement gives us design pressures that can be used to determine performance grades, even for high-rise buildings. And generally, the results are considered conservative, and safe to use. And so this gives you basically a way of putting together a proper glass budget, even on a large building, when you need to consider the wind loads. It gives you something to work with. So
we're starting to see engineers. When I first started in this business, the engineers were calculating their design pressures based on structural commentary and the language in the code. But Fenestration Canada's online performance grade calculator has been so successful, it's such an easy tool to use, that engineers have forgotten how to use structural commentaries and the code language, and they tend to just go use the A440S1 as their specifying tool. So
I think we should say some engineers.
Some engineers, that's right.
Yes, let's be careful. This is not a coast to coast stampede phenomenon, I don't think. But your point is well taken. Is that if there's a shortcut, simplified method, people are inclined to go with it. Of course, it's the professional responsibility of an engineer to independently validate whatever alternative methodology they're using, because they're actually taking full responsibility for the design. So they need to be confident that if they're using a tool that simplifies that for them, it's a tool that they can trust.
Well, I think the situation that I described applies more to engineers who are working in building science, not the ones who are doing the review of the structural aspects of the glass, But when you have that on your specification that, you need a NAVS rating of PG 35 and all of that kind of stuff, it can make things interesting down the road.
So that covers the glass design topic. I wonder if we have questions from our folks online about this.
Now, I believe you're able to raise your hands.
Yeah, so if people wanna talk with us, they can raise their hands and join the conversation, or they can use the Q&A button. At this point, we don't have any questions, but we're just asking now, so maybe we can
Sure.
give a second.
While we wait, Dave, this content, to some people who saw our earlier presentations earlier this year where we discussed this, they might say, well, you already told us this a few months back. But I think we didn't quite have it right the first time around. We were generally on the right track, but not in detail. So I would say the content of this presentation supersedes what we had earlier shared. We shared you the best knowledge we had at the time. We have since then been able to dig into this more deeply. And this presentation is more up to date and is now, as several engineers have confirmed, that what we're telling you is not incorrect.
Mm.
So this is now the more accurate presentation on the topic to the information we've shared earlier.
Practice makes perfect, Al.
Practice makes perfect. That's right.
And review by people in the industry.
Yes.
So where are those hands, everyone?
So we do have one question coming in. Patrick's asking, how much wind does a window have to resist? A hurricane, really bad storm?
Well, I think the simple answer to that question, I use the 1 in 50 hourly wind pressure. The code doesn't require buildings to withstand natural disasters. Otherwise, all of our buildings would have to be designed to withstand a tornado. That would make your buildings a little bit cost ineffective. So it's reasonable conditions. And then so it's worth pointing out that they're quite conservative, the specified wind loads, because they're basically assuming a worst case scenario with the gust factors, internal and external gust factors and pressure coefficients. The windows are not just withstanding the wind load, like if a window was sitting in an open field and not part of a building. They're withstanding suction pressures due to wind going around the corner of the building, creating suction like on an airplane wing, and pressurization of the interior of the compartment due to something like a patio door being open. So in order to experience these pressures in real life, you need to have your windstorm going and you left the window or door open, and it just happens to be a corner window and the wind is blowing from the right direction to create the suction. So they're pretty conservative.
And this is happening with that 1 in 50-year wind load.
At the same time as that 1 in 50.
All happening at the same time. So,
yes.
So we're designing for a confluence of factors where essentially all the bad things line up and happen at the same time, which is a condition that is relatively infrequent.
And I think this answers the question about before NAVs. We were dealing with, and the Canadian supplement, we had a system that was full of loopholes, but that you didn't hear about, residential windows blowing out in the real world. And it was because, they're not at the corner by the roof under all of these worst case scenarios for the most part. So we have in the past gotten away with things like not having proper mullion reinforcement and glass thickness. And we have some windstorms in Calgary, pretty serious ones, and the only thing I've ever heard of is the windows at the corners of the high-rise building. The glass breaks and creates a hazard to pedestrians out on the street. I've never heard of a residential window blowing out. So I think we can be confident that these are pretty conservative design parameters that are being used.
Okay. Well, that's the question we had for now. So I'll let you know if we have more on the way.
Sure. So next topic we're going to tackle is a newer topic. We've mentioned it in a high level way. We're now going to address it in a little bit more detail with some practical applications from the real world. Glass design for guard loads. So we've told you before that the code requires walls to act as guards. For some of you, if you haven't heard our presentations from earlier in the year, you may have missed that. But wind is not the only design load that applies to walls and windows. The code also requires walls to act as guards that can prevent a falling injury when there's an elevation difference of 600 millimeters or more between the interior walking surface and exterior surfaces or the ground. NBC Article 41516, by the way, that's in Part 4, which is the structural design part of the code. It actually specifies the loads that walls acting as guards are required to resist. And it requires them to resist a lateral design load specified in the code, or 0.5 kilopascals acting outward, whichever is the more critical load. This load is applied at the specified guard height, and that can change. If you're inside a dwelling unit, the guard height in the code is 900 millimeters. If you're not in a dwelling unit, if you're in a public space or an office space or any other occupancy, the guard height is 1070 millimeters. Now, this requirement can apply to windows when their windowsills are below the guard height. And again, in a residential dwelling, the guard height is 900. In other locations, it's 1070. What that means is that the glass in the window or a horizontal mullion has to be designed to resist the same guard load as the wall. Now, this is a very clear requirement in the code. Any engineer working on window design in larger buildings would be expected to take this into account when they're evaluating the design of the fenestration system.
And I would say, you know, it's changed a little bit.
The same requirement applies. Yes, Dave.
Sorry. So this has been an official code interpretation in BC since 2006. And when ABC 2014 came in, we asked the Building Subcouncil of the Safety Codes Council whether this was the interpretation in Alberta. Could they publish an official code interpretation stand data? They said that's not the way we see it in Alberta, and the code language was murky. But as of NBC 2015, there's some code language that makes it quite clear, and Al is going to review this code language a little later in the presentation.
Thank you, Dave. And you know, honestly, I think what we're telling you is what's in the code. It doesn't mean that this is consistently being enforced. It doesn't mean that all parties have been doing this in the past. It doesn't mean that even all parties agree. But if the people who don't agree have probably not looked at these portions of the code recently. Maybe they're relying on past experience on previous code editions. So again, there are people who may challenge whether this is really required, but what we're telling you is it's in the code, and it is something that engineers that specialize in fenestration design in large buildings are very much aware of. And it's something that if you do work in small or large buildings, could come into play. So the same requirement applies to windows in stairwells. And this is clear in Part 9, sentences 9, 8, 8, 1, 6, and 7. And this is one area where I think window manufacturers have probably run into the guard requirement for windows, Dave, is in stairwells.
That's where people are familiar with it, and that's where it'll be enforced in Part 9 buildings.
Because that's where it's explicitly stated as a Part 9 requirement. So
that's correct.
This is where the building officials have been more aware of it, and that's where they've paid more attention to this requirement.
And we are borrowing from these sentences to get our 1070 and 900 millimeter requirements for windows in walls that need to meet guard loads. Because the language regarding windows and walls and that need to meet guard loads is not specific to this type of information, but it stands to reason that the same principles that apply to windows and stairwells should also apply to windows and walls that need to act as guards.
So we're asking on this slide, is this really true? Because I know I've been involved in projects in the past where window manufacturers have said, no, that's not true. This can't be true. I've never encountered this before. But yes, it is true. Does the code require windows to resist guard loads? As Dave mentioned, there are code interpretations in BC. There's also a code interpretation in Ontario that was just like that, Dave, that established that windows should resist guard loads when their sills are below guard height, and where's a height difference of 600 millimeters or more from your interior walking surface to the exterior. And additionally, Dave, you have found the same requirement or a similar requirement in the 2015 code structural commentary I, which not only refers to the guard loads, but also confirms that the guard load has to be added to the wind load when you're designing glass.
And at FanBC, I was giving a number of presentations saying, is this really true? Where I was on the skeptical side.
Okay.
And then an engineer said, have you read this note from structural commentary? Yes, it is true, Dave.
So this is an area where even engineers practicing in the industry have taken different sides on this position. And I guess it's that text in the structural commentary that is, you know, it's not in the body of the code, but it's clearly meant to be the intent of the code. And this is the specific clause, basically stating that when there is a condition where a guard load would apply to a window, then the guard load requirements of NBC Article 41514 or 41516 are applied in combination with the wind load requirements in accordance with NBC Table 4132A, where the height of glass panels, yeah. And so basically these guard loads only come into play when the height of the glass panel or the height of the windowsill is below the guard height. So part 3 of the code says that stairs and ramps, landings, handrails, and guards within a dwelling unit shall conform to the appropriate requirements in section 9.8. So basically in large buildings, this applies as well as in part 9 buildings, because part 3 addressing the subject of stairs, ramps, landings, handrails, and guards for dwelling units. If you're in a dwelling unit, these part 9 requirements apply. And basically they are glazing installed over stairs, ramps, and landings that extends to below 1070 millimeters above the surface of the treads shall be protected by guards or be non-openable and designed to withstand the specified lateral loads for balcony guards. But that's in stairs, ramps, and landings. The next sentence says, in dwelling units, glazing installed over stairs, ramps, or landings, and then glazing installed in public areas that extends to less than 1 meter from the floor and is located above the second story. So these are various places in part 9 where the guard requirement applies. Well, then when you're going to do the calculations, what loads are you dealing with? And the three possible guard loads are defined in this NBC sentence, 415.14.1. The first one doesn't really apply because it's for stadiums. It's a very high load that you would expect to have on a guard. If you've got hundreds of people crowding and pressing against a guardrail, you're going to have quite a much higher load than just an individual person or a couple of people, pushing on the guardrail. So it's cases B or C here that apply. And the loads would be 1 kilonewton applied at any point to produce the most critical effect. This would be in the case of stairs or access to equipment platforms or similar areas where the gathering of many people is improbable. The gathering of many people would be condition A, the guard, grandstands, stadiums, bleachers, and arenas. And then for other areas, the guard load would be 0.75 kilonewtons per meter. That would be like a linear load, or a concentrated load of 1 kilonewton per meter applied at any point so as to produce the most critical effect.
Right. That was a typo from another presentation, Al, that you caught, but you never corrected it in your slides. It's 1 kilonewton, a concentrated load, not kilonewton per meter.
Oh, this one, oh, item C, right?
Yeah, that's right. And you noticed it while we were doing our last presentation and
Ah,
left it in there for this presentation.
all right, all right. We'll fix it. We'll fix it this time. Thank you.
So, guys, I do have we do have a question. So I'll
Sure.
just so Rick is asking, are architects designing building and specifically window configurations to these codes?
I think they are, and we've got some slides on this a little later on that will cover
Okay.
that topic.
Okay.
Although in a conversation with David Vidos a week or two ago, he was saying that architects do need, not all architects are aware of these requirements, and that he felt that architects actually need to be educated about the requirement for these windows to resist guard loads as well.
Well, especially in Alberta.
Okay. So basically, when you're designing for these guards loads, there are two cases you have to consider, and the more critical of the two would apply. So one case is 1.4 times the wind load plus 0.5 times the live guard load. The other case is 1.5 times the live guard load plus 0.4 times the wind load. So can you discuss how that works in as an
Sure.
engineer?
Sure. From that table that was earlier in the presentation, you've got principal loads and companion loads. And the idea behind this is the building code doesn't require you to design for the worst case scenario simultaneously. So one worst case scenario is you've got the 1.4 factor from the wind load, which would be in the middle of your storm, but you only have to use 0.5 times the guard load, because they reason that it's improbable that somebody's going to run up against a window in the middle of a windstorm and bump against it and fall through applying the full guard load to the windows. I personally would be kind of staying away from the windows if they were rattling and bowing out and all of those types of things that you would see in this kind of worst case scenario. But the controlling factor, unless you got very high wind loads, it's going to be 1.5 times the guard load plus 0.4 times the wind load. So they're saying that you're not going to be having a terrible windstorm happening at the same time as the window is required to meet guard loads. And you can find this reasoning throughout that table, that part of the code in part 4.
Thank you. So here's some examples of how the guard load, where the loads would be applied and what the loads would be in two cases. We're going to look at a window where a mullion has been provided at or above the guard load to be the principal means of resistance for the guard load. And we'll look at a fixed window where there's no horizontal mullion in the vicinity of the guard height, but we're relying on the glass. Do you want to discuss this slide, Dave?
Yeah, so in answer to the previous question, we think that although some architects might not be cognizant of the reason that they're doing this, we get a heck of a lot of plans for these buildings where based on the sill height, the horizontal mullion just happens to be placed either exactly at the guard height or just above the guard height. And the glass that makes up infill panels below is smaller than certain sizes. And they may be doing this because traditionally, that's what they've been supplying and they've never questioned it. But what we see here is the mullion has to take the primary guard load 1.0 times the guard load inward and 0.5 times, outward, and 0.5 times the guard load inward. And then the infill panel only has to take half of the guard load, the 0.5 kilonewton over a 100 by 100 millimeter area, in theory. I think our other slides, if you move on, we have got some examples.
Yeah. So, and also the language is that the point at which you apply that infill load is where it's located for the most critical effect, right?
That's right. And an engineer at RDH advised that he locates it horizontally at 1/3 of the glass width because he found that that creates the most critical effect. So that's what Al has illustrated here, and that vertically it's at the guard height.
And here's the case of a fixed window where guard loads apply.
So in this case, it's going to be tougher on the glass because it needs to meet the full guard load, and you're going to find, for example, that 4-on-4 glazing typically is not going to do this for you, and you need to bump it to 5-on-5 because you don't have that horizontal mullion to take the full guard load, and the glass has to take the full guard load.
Now, is there any requirement for the glass to be tempered if the window
Well,
is
yeah,
adjusted for
so
guard load? In other words, is there a tempering requirement for safety, or is the tempering would only be required if it was required for strength based on the?
it is definitely required for strength because the capacity, the stress capacity of annealed glass is 25 megapascals, and for tempered it's 4 times, and so you're never going to get it under any scenario with the annealed glass.
Well, I mean, if this window was only 2 feet wide, is it possible it might work with annealed glass? Say 6 more, 6 more.
Well, I started using an online available free software recently and playing around in there. I'm thinking that the answer is no. I have not done an exhaustive comparison of all sizes, but it doesn't seem to reduce the stresses greatly that the light size is smaller.
I see. Okay, that's interesting. So these are the conditions that engineers would be analyzing with respect to guard load on the window, right?
Correct.
And they would be adding this guard load to the wind load using one of those cases in that calculation.
Correct. And I think most engineers don't bother with case 1 because they know it's going to be the less critical case unless you've got some extraordinary wind load occurring.
Right, okay. So windows acting as guards.
Just a second, guys. I have a question here from John. John's asking, are the load on guard requirements the same for residential suites, and are they different from a fixed window versus an operable window?
So what we are getting is zero enforcement on Part 9 buildings, but residential suites within non-Part 9 buildings, yes, absolutely, it applies. And we've got some slides that address the latter part of the question.
Yeah, could you just repeat the question again, Steph?
Yes, give me a second. Are the load on guard requirements the same for residential suites, and are they different from a fixed window versus an operable window?
Oh, okay. So in other words, in all residential suites, you're dealing with the same guard load, regardless of a large building or small building. Is that right?
Well, fixed versus operable, I believe we have some slides that address that.
Well, yeah, I was thinking just in terms of the load.
Yes, they are absolutely the same. It's just the guard height is lower in dwelling units,
right,
and then it is in public areas.
So I don't think the occupancy makes a difference for guard load, right? It could be in a public area.
Right. Yeah, the guard height is higher in a public area than it is within a dwelling unit is the language that they use in the code.
Yeah. So there are, in other words, you could encounter a guard load in an office building. You could encounter it in a hallway, in a residential building. You could encounter it inside a residential unit of a building. But whenever you're designing for guard load, it's the same guard load you're designing for. Would that be correct?
Correct.
Yeah. So regarding enforcement, generally, we're not finding this being actively enforced because, you know, it's in part 4 of the code. This requirement for walls to act as guards and for windows in walls to act as guards is in the structural part of the code. So generally, building officials are not monitoring part 4 compliance issues. So unless they see it through, now part 3 of the code does point you to part 9 for within dwelling units, right? So, so clearly within dwelling units, you would think that this would be considered even in large buildings, but it doesn't seem to be. It seems to be more, would you say it's more noticed by building officials in part 9 buildings, particularly in stairwells?
Absolutely. The building officials in Part 9 buildings are looking for this in stairwells, and they're not looking for it anywhere else. And then on a non-Part 9 buildings, you expect there to be supporting registered professionals, and they're obliged to look at it. So the building officials tend to cede the inspection to the supporting registered professionals to do professional design and field review. And then they assume, because you've got those supporting registered professionals involved, that everything's being done properly.
So many building officials are not aware that the code requires windows with sills below guard height in general to support guard loads. They tend to focus on the stairwells when they think of this requirement.
I think that's fair. Yep.
Yes. Even though under part 4, it's something that would always apply to any window anywhere.
That would be the strict interpretation, but unless there's an engineer involved in your building, that's not going to get enforced.
Well, but this is why I think it's important for our members still to know that, because if you happen to need to get an engineer involved with respect to the glass or framing design of windows in a Part 9 building, that engineer will likely be aware of this requirement and apply it. So I know I was involved in a project where a manufacturer had a window system that wasn't NAFS tested, and the consulting company I worked for was hired us. This manufacturer hired us to help them resolve their compliance issues, and we looked at their available testing. We looked at this and that, the other thing. Long and the short of it is, we performed some job site water testing to validate the water performance of configurations that had not been tested in the lab. They had tested products in the lab. It's just that they had configurations on this house of very large windows that were not tested in the configurations supplied to the house. So, there was some NAFS testing. So, but engineering was required to address the structural issues of the window system. And the engineer involved had to address the guard issue, because an engineer cannot not address it, right? If you're designing to part 4, if you are an engineer, if you're aware of the guard requirement on windows, you can't just ignore it because it's a Part 9 building. So in fact, it turned out that it led to the glass having to be replaced in these windows, because they just weren't strong enough for the guard load condition. So I think it's important for people to realize that because it's a part 4 issue and it's a Part 9 building doesn't mean it won't affect you. It will likely affect you if you need to have an engineer involved in that project.
And it is possible for a safety codes officer on a Part 9 building to demand a design according to parts 4 and 5. If they notice that it's on the top of a hill or escarpment in a high wind area, it is within their authority for them to say, no, standard Part 9 conditions are not going to be sufficient for this building. I need some engineering done.
Right. So in other words, there are other, even outside of yourself, a building official may require engineering for some condition that then would involve you in having to be fully compliant with these Part 4 requirements as well. So we think
we do have 2 questions.
Certainly, yeah.
Yeah. So Pauline's asking, do all windows as guards need to use tempered glass, whether they're mauled or not?
And we got some slides coming up. There are some engineers, but because the language is just that one paragraph in structural commentaries, that leaves it open for interpretation. And engineers practicing in the field have some interpretations that allow them to not unnecessarily have too much tempered glazing in the buildings, and we'll get to that a little later in the presentation.
Okay, yeah, that's coming up.
And we have another one.
question?
Do you want me to, maybe I can ask this one and see if it's more relevant for now. So how do you suggest that the residential industry educate inspectors to inspect for guards in general?
Well, yeah, the residential industry, that's kind of a tough one. In Part 9, I'm not sure that we want them to.
Mhm.
I think that yeah, Part 9 buildings tend to have falls that are not quite as high as non-Part 9 buildings, and I think that safety codes officers would be looking at the types of accidents that are occurring that are causing real injuries to real people. And that's primarily children falling out of windows that don't have sash restrictors that should have sash restrictors. There's probably not really any cases in Part 9 of people breaking through windows and falling to their deaths because the window wasn't designed to meet guard loads. So, you know, even though technically, you know, this is a code requirement, do we want to start lobbying for full enforcement at this point in time? I would suggest possibly not.
I think our focus here is just to help our members appreciate that this is something they could face, and they need to be prepared to know that it's something they could face. So so I think it's better to know and be prepared and to anticipate than to not know. So
Sure. Well, actually, something just came to mind, Al, and the 2020 national model codes will have increased the guard height in Part 9 buildings from 450 millimeters to 900 millimeters. So that might solve the problem right there.
sorry, the guard height from
Well,
450.
it's not the guard height per se, but the height at which a window needs to be protected. An operable window needs to be protected by a sash restrictor.
I see.
Will increase from 450 to 900 millimeters, which will also place it above the guard height. So I think
I see what you're saying.
this
Right.
will be a self-solving situation for units with operators in the 2020 national model codes.
Right. So that'll be coming in 5 years. Okay, roughly. So maybe 3-4 years. Yeah. So awareness of this requirement varies across the country. We know that many Canadian fenestration consulting engineers are in general consensus that windows must be designed to resist the code specified guard loads. On single family homes and Part 9 buildings, you will only encounter it if you need to engage an engineer or someone requires you to engage an engineer for some reason. And so that's basically, you know, the state of the art. This is where we're at. And again, it's just, we're just advising you to be prepared for it. And now, Dave, these are some of the examples that you've encountered, and turn it over to you here.
Yes, absolutely. So engineers want to be reasonable. They don't want to push up the cost of a building. So we typically see on the plans, you know, that there are operable units that are below the guard height with horizontal mullions. You know, so the unit on the left would be typical for a multi-light unit in a non-Part 9 building. So they seem to be designing this way for other reasons. And so you notice that the operable unit on the left of that left unit is permissible, provided that it has a sash restrictor. And there's no requirement for that sash restrictor mechanism to be able to resist the full guard load. And something tells me that if you were to push on an operable window that was in the unlocked and open position with the full guard load, you would probably break that sash restrictor. So based on this, engineers operating in this field have a rule of thumb, at least the engineer that we use, is that if the opening that would be created by breaking the glass or busting the sash open is less than a rather arbitrary number of 600 millimeters or 24 inches, they're willing to permit that light of glass to be non-tempered, and they're willing to allow operable units by that same light.
Now, but you're referring to 600 millimeters in height?
Well, yeah, 600 millimeters in any direction. So if the opening was narrower or shorter than 600 millimeters, excuse me, you know, they are basically using their engineering judgment to say, I can't envision somebody going through this opening. You know, first they'd have to break it with an axe, and then they'd have to crawl through the broken glass to plunge to their deaths. So they think that's not reasonable, and giving the practices that apply to operable units, they're willing to waive the requirement for the glass, the infill glass, to meet that guard load, provided it's a small enough unit.
So that would be the infill guard load, right?
Correct.
Because the horizontal mullion is at guard height, so the glass would only be subject to the infill load. And what they're saying is if it's too small to actually be experiencing a human guard impact, they would ignore the application of the
I've
glass
never
clause.
had them explain it to me explicitly, but this seems to be the rule of thumb.
Okay.
And so what you see, we see project specifications and elevations every day where the unit on the left is a very, very common unit, and the unit on the right is less common. And then we say, listen, you know, this unit on the right is going to need to be 5 mil tempered in to meet guard loads. You sure you don't want to, you know, put a mullion or something? Well, that's expensive as well, right? So they you know, so it's up to the building designer and the architect to try and design around requiring too much tempered glass in the building.
So,
Yeah, and so this is some verbiage that I added, so which is basically what I just described. So nothing is said about windows in the open position having sash restrictors that are capable of withstanding the prescribed guard loads of, in the case of an infill, 112.4 pounds. In a case of the main load bearing, 225 pounds, basically. You know, thinking of the kind of sash restrictors that are available out there, you know, I can't picture, you know, you push on the corner of the sash and the sash restrictors at the opposite corner, like the top corner or the bottom corner, with 225 pounds of force. Something tells me that that's not going to meet guard loads. So again, this is a rule of thumb, and it's up to the engineers who are signing and sealing shop drawings and building code letters of assurance, you know, whether they're comfortable with this and willing to give that kind of a break.
we have another question here. John is saying, so therefore the window on the left must follow guard loads, whether it's fixed or operable. And then he asks, in a public area or in a residential suite?
Well, yeah, I think it's either. It's just the guard height is going to be different in the two instances.
Okay.
Now, you tend not to see, you know, the operable windows in the public areas, would be my experience. And they tend to be in stairwells, in which case the language is very clear that they need to be non-operable and designed to resist the lateral design loads for balcony guards. So the principles that I'm discussing here would not apply to windows in landings or stairwells, where it's very well understood. It's just because the code language regarding windows and walls needing to act as guards is just that one paragraph that we reviewed earlier on in the presentation, and it's in structural commentaries, which is not a part of the main body of the code.
Well, the requirement for windows to act as guards is in the code. The combination of live load with wind load was in the structural commentary.
Yes.
No, because part 4 was clear that the guard load that applies to the wall also applies to the window when the sill is below the guard height. So, so the requirement for any window to be subject to guard load is in part 4.
Yeah, I would say that's a fair statement. Part 4 with the reference to the language in structural commentary that made it 100% clear.
And now, second part of John's question, in a public area or residential suite, might be that in part 9, it talks about public areas, that the guard load windows are subject to guard load in a public area. And so his question is, what about a residential suite? Would that also apply in a residential suite? And that's where part 9 doesn't tell you it would have to apply in a residential suite, but an engineer who was working on the project may say that, yes, this is a condition where there's more than 600 millimeter drop and the windowsill is below the guard height. So this window does need to resist the guard load.
It's a fair summary.
Another question here from Rick Zolmer. So the lower lights and the window on the left does need to be tempered? Please clarify.
The engineer that we work with would waive that requirement based on the opening being less than 600 millimeters.
But if it wasn't, if they were more than 600 millimeters, that engineer would be applying the glass infill load to the glass below the horizontal mullion.
That's correct. Because it's an interpretation and a rule of thumb, they have a little bit of leeway whether they're comfortable or not. So they might look at where in the building that window is and factors like that. But they are willing to be a little bit flexible. But I'm sure they wouldn't allow 900, for example.
So I think that basically the requirement for the mullion to resist the guard load is clear. Whether or not the glass below the guard height should be an infill load application, I think that's a matter of engineering judgment, isn't it? Or is
Yes,
that right? Because
absolutely.
the code doesn't specifically say that, but the engineers who are practicing here are saying, well, this horizontal mullion is functioning as a guard. So the engineer would say, well, it's reasonable then that the load, if this was a glass guardrail and not a window, the glass below the guard would have to support the glass infill load.
Absolutely. But then in a
Right?
glass railing with an infill, that infill is going right down to the floor.
Yes.
Right.
Well,
so if that glass broke, then a toddler could take a plunge, right?
right. But you could also have a pony wall with a guardrail on it, right?
Right.
So in other words, you could have this exact condition as a guard on a balcony with 18 inches or 24 inches of glass sitting on a concrete wall or something like that.
Yeah, I don't think with respect to actual railings and guards, I don't think they'd be able to waive any of the requirements.
That's right. It would be very clear, because if it was actually a guard, then the guard must have glass that can support the infill load. I don't think the requirement for the window to support a guard load, I don't think there's any, that does not automatically turn the window into a guard. It just means that just as the wall is not formally technically a guard, so the window is supporting the guard load. And this is where some engineers would say, well, since it's functioning like a guard, I think the glass below the horizontal mullion should be supporting the infill load. But I think could be a matter where engineers differ. Would that be?
I think that's a possibility. So back when I was on the skeptical side of the fence, I was making points well, it's a dual glaze sealed unit. It's not a single light of glass, held with clips like in a guard infill, right? And so, what really are the chances that someone's going to break through the first light that's tempered, then through the second light and plunge to their death? So I was actually a little bit opposed to this at one point, and trying to argue for something more reasonable. But then NBC 2015 came in with this wording that made it crystal clear in structural commentaries.
Right. So I think we still had some more questions coming in here. So Rick has been asking if the lower lights need to be tempered. We can't say that definitively. I think that'll be the engineer's judgment. Would that be right?
Right.
Okay. Another question from Adam: can we use 3 millimeter annealed for windows that are under guard height? We have TIST reports that 3 and then we have test reports that 3 millimeter annealed glass meets log. I'm not sure what he means by that. LOG.
Well, at one point I thought that if you tempered the glass, it was always going to meet guard loads. But then I found out there's finite, and really the only way to analyze it properly as an engineer is by using finite element analysis. And an engineer pointed me to a particular software, and so it will not meet guard loads at 3 millimeter annealed, not even the infill load, not at any size. I know it needs to be tempered. And we have some slides on using that software if we wanted to move to them.
Yes, I just
just so
there's
you
one
guys
more
know,
question still.
yeah, before we move forward, just for time's sake, I think the other session right after us is going to start soon. So
Okay.
just so you know, like, so if you want to.
Okay, let's move on
themselves.
then.
Yeah.
Let's move on, and
But we can still answer the question, but I just wanted to point out.
Sure. Well, I think we get to these other slides that'll kind of answer the question.
sure.
Okay.
Yeah.
So the ones with finite element analysis. So if you could go further. Okay, so this is a software program called MIPLA ISO. And in this particular case, so we are looking for a maximum stress of less than 100 MPa, which is also newtons per millimeter squared. And this is a 4 mil on 4 mil IG unit. And it's not showing the size on here, but it's relatively large size because there's your 100 by 100 millimeter low guard load right there at the guard height in the middle. And so it's not making it. Now, if you go to the next slide, 5 mil on 5 millimeter is at 104.76. That's just above the strength of glass. And now remember, I'm doing this work because I want to predict what the third-party professional is going to ask for glass thickness. And I know that the free version of the software is slightly more conservative than the fully paid up version of the software. So I reckon it's going to have a better rating, so to speak. It'll say a stress under 100 megapascal. And so by this logic, I'm saying the 5 mil will pass. Now, if you were to do this for 3 mil, it's going to say, hey, you're at 300 megapascals, the stress in the glass. So using this type of software is the only way to determine that. Test reports are not going to determine that, unless you're using actual guard loads, impact loads, and that type of thing that are used to qualify safety glass. I think there are some test methods that can demonstrate that, but they're impact loading type test methods.
So, so this was the input screen, I guess, for the.
That was the input screen, yes. And you
for
see
the
what we're doing?
project.
We've got in this case, we had a 1.4 kilopascal suction wind load, and at the same time, we combined it with 1 kilonewton guard load. And I reversed the signs so the arrow's reversed. It's inside to outside load, and I used the wind factor of 0.4 from part 4 and the point factor of 1.5, and then it calculated the maximum stress of 163.69 at that location. So red means higher stress. You get down to blue, and that means lower stress, and they're showing it to you on the left. So this would be, one of the reasons why a smaller light is not necessarily going to be stronger with regards to this, because it's where the point load is being applied that the glass is subject to those maximum stresses.
Yeah, there's a couple questions here. Well, Rick's asking if the presentation will be available, so I can answer that. Everything that you see here that's live is going to be on demand anyway in the platform. So, you can always come back and watch it. I don't know. Did we answer to Rick? No, we didn't get to that question.
So somebody is asking what the software
Yeah.
is. It's MIPLA ISO, MEPLA ISO. If you type that in, it'll take you to a website in Germany where they will offer you the free version, and then keep pestering you to upgrade to the fully paid version.
So it's
3,500 euro. It's not a cheap piece of software. I'm not sure if I'm going to invest in the full software just for my purposes, but
Okay.
yeah, and it does all sorts of other stuff more than just Windows.
And we had another question I think we didn't ask yet. So Rick is also asking, what's your opinion on weighing safety against broken glass versus fall potential?
It's not required to be safety glass. It's not in a door. It's not a side light to a door. It's required to be tempered glass in order to meet the loads, which happens to also make it safety glass.
Okay. So, well, as I said, we're starting another panel in like 15 minutes. I think both of you guys are going to be on that panel also, right?
Yes.
Okay.
Yes.
So
Good.
The fun continues.
Thank you, everyone. And I'm sure we'll be discussing this issue again in future times, but hopefully this will just to help broaden awareness of this issue to our members. Thank you.
Perfect. I'll see you in a couple minutes.
Okay.
Thanks.